So yesterday, I ended up by discussing the Gauss theorem and the fact that you cannot change the Gauss curvature of the surface without you cannot deform a sheet and change its Gaussian curvature without straining it. And so for since we are, lots of plate theory is interested in flat plates, and as I said, because stretching energy, the stretching modulus is large compared to the bending modulus, we will there is a special interest on the surfaces that are isometric to a plate. So surfaces with zero, with vanishing Gauss curvature. So what I will do first is to characterize these surfaces, okay? And we'll see that they are surprisingly easy to characterize. So I will restrict myself to surfaces that are close to a plane. So what we want to explore on the surfaces defined this way, x, y, and this function zeta of x and y. And I want to know what are the conditions on zeta for this surface to be isometric to a plane, or to have equivalently to have a zero Gaussian curvature. So for this, I will start by introduce the curvature tensor. Cij, di, this is di, dj, zeta, because this surface is close to a plane, so I don't have to use the covariant formulation. So this C, it is symmetric. Then its trace is the determinant of C. This is the Gauss curvature, and this is zero. And the trace of C is, I define it as 2H, and H is the mean curvature. So if I, the 2H, I can, assuming that the mean curvature is not zero, I can take the 2H out of I can factor out 2H in C, and I can always write C this way. So this I will not prove. H actually depends on the coordinates. And then I can parameterize the matrix with sin square phi minus sin phi cos phi. Here the same because it is symmetric, and here cos phi square. And you can check that this matrix satisfies all this. Okay, so there is this phi, which is an angle, and depends on the coordinates. Okay, so you can always write this matrix. So if you take 2H out of C, you have a symmetric matrix with zero determinant and trace one. So there's only one free parameter. This free parameter is phi. So the functions, then I want to get a condition on phi and h. And actually, phi and h, they should verify the compatibility condition. So compatibility in general means that it is a condition coming from the fact that these quantities, they are not independent quantities. They derive from lower, say, lower level quantities. And in this case, this is zeta is the low level quantity. So actually, the compatibility condition for C is simple. C ij is the second derivative of zeta. And so I can compute, I mean, derivative of C. I can, I have that, for instance, dy cx x is equal to dx cx y. Okay, because these are derivative of zeta twice with respect to x and once with respect to y. Okay, and the second one is dx cy y is equal to dy cx y. So these are the compatibility conditions. So I won't do the full calculation actually. So in this calculation, you can put you can plug in this expression for C, okay? Then expand the derivatives, and what you will obtain when in these derivatives. So here you see that you have in C you have products of h times functions of phi. Okay? So in the derivatives you will have terms with constant phi multiplied by derivative of h plus terms of constant a of h multiplied by derivatives of phi. Okay. So you can, doing that, you can actually eliminate, I mean, this is all equal to 0, and you can, there is a way to eliminate h from the equation, and you arrive at an equation, you can arrive at an equation for phi, which is cos phi dx phi plus sine phi dy phi equal to 0. So here, expanding and combining, we arrive at this. Okay. So I don't know if you are familiar with the method of characteristics. So the method of characteristics, you can, I mean, this is a first order nonlinear PDE for phi, which as it is, yes, and you can try to solve it with the methods of characteristics. So the method of characteristics says that you will define here, you write it as Vx dx phi plus Vy dy phi equal to 0, where Vx and Vy are this cos phi and sine phi here. And then you introduce the characteristic curves, which are x at, which will satisfy. So these curves are parameterized with an internal parameter s, and they should satisfy x hat prime is Vx of x at s, y at s, and same for Vy. Okay, and then if you consider phi, okay, so maybe I will solve for, no, I will, sorry, I need to do that. Phi at, you can define phi at of S, which is the value of phi, which is the unknown on the characteristic curve. So this is phi of x at S, y at S. And what you can show is that phi at prime of S, so if I take the derivative of this with respect to S, I use the chain rule here, and what happens is, what appears is exactly what I have here. Okay? And so this is Vx d x phi plus Vy d y phi all these taken at x at s, y at s, but because of the phi solution, this is 0. Okay, so this means that on these curves, phi is constant. This characteristics. This is how these curves are called. And so now I will solve for this. Since phi is constant, then Vx and y and Vy are also constant. Okay, so from this, so then this is easy. These characteristics are just straight lines because these this is actually the tangent vector that we have here, and the tangent vector is oriented along, with an angle, just with an orientation given by the angle phi. Basically, if you have your xy coordinates here, it means that you can, so imagine that this is your the domain where your sheet is defined, and you can the characteristics are like this. So phi is constant along these characteristics. So now I will compute the shape of the curve along these characteristics. So now we just have phi, but I know nothing about h, for instance, along these characteristics. So what I want to compute is, so the height along x, so this is zeta at of s, which is zeta of x at s, y at s. Now, if I want to, so I can define zeta this way, but what I will compute is I will compute the second derivative of zeta. So what I get here, so I can derive, so it's d over ds. I will first do the first derivative and then the second. So when I derive the first, I have x at prime s dx zeta of x at y at plus y at prime of s dy zeta of the same thing. And then I have to derive this with respect to s, but this is easier than expected because the second derivative of x at and y at are 0 because these are straight lines. So we end up just with x at prime s square dx zeta x at dx square zeta plus x at prime y at prime, and there is two factors like this, dx dy zeta, so this is the cross term, plus y at prime square dy square zeta. Okay, and so here I can use that y, this is cos phi square, and this is cxx plus 2 cos phi sine phi cxy plus sine phi square cyy. I use just the fact that this is second derivative is the definition of the curvature tensor, and what you find from this expression is that this is 0. So I will not try to do a drawing, but these lines, so this is the xy plane, but in the out of plane direction, they are a straight line also. Okay, they can have a non-zero slope, but still they should be straight. Okay, so my only approximation here was that surfaces were close to a plane, but what we have shown within this approximation, and that is actually true in general, is that surfaces with k equal to 0, which are also called developable, are ruled. Ruled meaning that they are made of these straight lines. Okay. So is the opposite true? For this, we have to. So we have okay this implication, and the question that we ask is what about the opposite? And so for this, we can define a ruled surface and compute its gauge curvature to see if there are constraints on the ruled surface. So for this, here I will leave the assumption of small slope. So I can define a ruled surface as R of these two internal variables, U and V, as, okay, you may think about it as the center line, A of U, and V is the transverse coordinate, or V is the coordinate along the flat direction. And this will be V, T of U. So here, V, A and T are vectors, okay? And without loss of generality, I mean, we can, of course, we can choose T to be normalized, for instance. And also, A can be shifted along the center line, along the line, along T. Okay, and also A can be reparametrized. So with this freedom that we have in defining this function A and T, we can assume, I mean, we can impose or choose the following conditions. So A prime equal to 1. So this vector will be normalized. A prime is derivative with respect to U. T is also normalized. And A prime T is 0. Okay, so I will not do the proof, but believe me, you can, this is something that is not too difficult to check, that starting from random, not random, but arbitrary A and T, you can change variables to arrive at this description here. Okay, so from this surface, we can compute the metric. So to compute the metric, we have D, U, R, which is A prime plus V T prime, D, V, R, which is just T, okay? And now the metric will be given by A prime plus V T prime. So this is a vector squared, 0, 0. And for the T, 0, because when I take the scalar product of these two, I have T scalar A prime, T scalar I prime, which is 0. And then T scalar T prime, which is 0 because T is normalized. Okay, and at the end, this one scalar this one, this is just 1. Any question? I mean, is everything clear here? Okay, so now we have to, what we have to compute is the Gauss curvature K, which was defined in full generality as U C V V minus C V U C U V with covariant and contravariant coordinates, but this can always be written since the metric, is diagonal. This is just G U U G V V times C U U C V V minus C U V C U V, sorry, square. And Cij here is the normal vector times di r di dj r. Okay, so everything here is, I mean, it's a bit messy. There are many terms and so on, but we can simplify because we want the Gauss curvature to be 0. So we don't care about prefactors. So this will be, sorry. So we want the Gauss curvature to be 0, so we can discard the prefactors here. So the prefactors are G U U G V V. So this is a non-zero prefactor, so we don't have to care about it. And the second one is when to define the normal vector. Here, the normal vector, I put a hat because it is normalized, but we don't have to take it normalized. We can take any normal vector. Okay. So this, this don't mean that I eliminate them. It means that we don't need to care about these constants. Okay. So here. So a simple way to construct a normal vector is to takedur cross product dv r. And so this is a prime plus vt cross product t prime. Sorry? T prime t. Okay, sorry. Yes. Thank you. And then what I have here, di dj of r. Okay, we'll write it as a matrix, but it will be a matrix with vector components. Okay. So if I derive twice with respect to u, actually I have a prime, which is I will have a double prime plus so a double prime, since a prime is normalized, a double prime is 0. No, actually, okay. The idea is that what I have here, I don't care because the second derivative with respect to v is 0. Okay, so here I have 0, and since c uu is multiplied by cvv and cvv is 0, this means that I don't have to compute cuu. okay? So here, whatever. This helps. And then the cross derivative, du dv of r, this is just t prime. So I have t prime here. So when I take the scalar product of this, so I take what I want to compute now is cuv, which is so k equal to 0 implies cuv equal to 0, and cuv is n scalar, this one. So it's a prime plus v t prime t scalar product with t prime. Okay, so this is a mixed product. So we can shift. So there are a mixed product of these three vectors here. So this one, then t and t prime. So I can permute them. So this is equal to t prime cross product a prime plus v t prime scalar product t. And here I have t prime cross product with t prime. And so this is 0. So I can remove this term. And I end up with, how do I write it? I have t prime, a prime. I will shuffle again the other way. I will have a prime t scalar product t prime equal to 0. So this means that the rule surfaces have to satisfy this condition for their Gauss curvature to vanish, so to be developable. Okay, so we can explore what it means. So locally, I mean for this to be 0, we can have either t prime is equal to 0. So if t prime is equal to 0, t is constant. This means that the vector giving the straight direction is constant, and this is locally a cylinder. Which is okay. So if, sorry? Oh. The question, so if t prime different from 0, then a prime, so can be written as, so for these three vectors to have, for this mixed product to be 0, this means that these three vectors lie in a plane. Okay, they are coplanar. So this means that we can write a prime as a function of t and t prime, as a linear combination of t and t prime. Okay, so we can write a prime of u is equal to lambda of u t of u plus mu of u t prime u. Okay, and this here I can shift the I will shift the baseline. We'll define a tilde, which is a minus mu t, and which satisfy a tilde prime. So this is a prime minus mu prime t minus mu t prime. Sorry, I'm a bit lost. A prime. don't know why I wrote that. It's oh yes, yes. Okay, sorry. Okay, sorry. So this is sorry. So this is lambda a prime is lambda prime. No. Okay, sorry. Yes, thanks. Thanks for your help. So lambda t plus mu t prime minus mu prime t minus mu t prime they mu t prime, and I have lambda minus mu prime t. Okay. Thank you. So then for this, so this is just, I just shifted the baseline, but this is the same shape. Okay. Now, if lambda minus mu prime is equal to 0, then a tilde prime equal to 0. And this means that the baseline doesn't move. Okay, and so this describes a cone. Okay, because a cone is a ruled surface with a common reference point. You should be clear the fact that a tilde and a do not actually have to be on the surface. Okay, when I define this, I didn't define the domain of u and v. Okay, so u and v in some is some domain of the plane, but they don't have to be the v, for instance. I mean, 0 doesn't. Maybe v equal to 0 is not in this domain. Okay, so this means that a of u is not on the surface. Okay, so the same is true for a tilde, which doesn't have to be on the surface. So the surface then is locally. So in this case, it is a cone, and if it is not a cone, then it means that a tilde prime is lies along the tangent vector t. So this means, so actually this a tilde prime is the tangent vector to the baseline a. Okay, so this is the tangent vector to the baseline is along. I mean, is collinear to the generatrix t. Okay. So in this case, this is called tangent developable surface. So locally, it should be one of these three types. Okay. So just the take-home message is that these surfaces are kind of controlled. I mean, we know that developable surfaces are ruled surfaces with this property. So just a simple example for this condition, maybe that will be clearer than all that follows, is that if you take a twisted ribbon, okay, so imagine you take a ribbon and you twist it. So here I will define it this way. So R of u and v. So we'll take a of u, that is, I don't even have to write this actually. So a of u will just be, say, u e z. Okay, so you have the baseline is along z, and then I twist it with a constant rate along z. So t of u will be cos eta u e x plus sine eta u e y. Okay, so this defines eta is the twist rate in this direction, and so we can wonder. I mean, we can wonder if this, what is the Gaussian curvature? I mean, is the Gaussian curvature 0 here? So does it satisfy this condition? So we just a prime is just easy. So it satisfies this condition. The tangent vector is cosine, is obviously normalized. And then, and these vectors are orthogonal. We satisfy this condition. We just have to compute T prime. And T prime is minus eta sine eta u x plus eta cos eta u e y. Maybe. Okay, and this is just, I will call it eta times t perp, because this is a vector perpendicular to t. Okay, and now if I compute a prime cross t, I have easy. I will do the full thing. E prime is equal to a prime cross t. You can put the eta factor here, dot t perp. And now it is clear that this is not going to be 0 because e prime is along z. So this vector, this is the vector rotated. So actually, I think this is t perp. Because you take, you have the z vector multiplied by the vector t in this plane. So you rotate the vector t, and you will end up with a vector perpendicular to t and perpendicular to ez. So it's still in the xy plane and perpendicular to t. So this is proportional to t perp. And so this is eta different from 0. So this is what is avoided. The generatrix cannot turn around the baseline. Yeah, actually, I spent a year working on the twisted ribbon without knowing that. Okay. Maybe this class is not that useful. It's good to know. Yes. Oh, thank you.
You write A prime is equal to lambda t plus mu t prime. Didn't you assume that A prime was perpendicular to t to begin with? So why do you have that lambda term in there?
Interesting. Okay, so I guess this simplifies things.
Yeah.
Does it make everything wrong? Makes everything simpler. So it's okay. Yeah, so lambda is 0. But it shouldn't be along A prime. If I take the scalar product of this with t, if I take the scalar product of this with t, and I say this to be 0, it imposes, since that t prime is 0, it means that lambda should be 0. Okay, so. You're perfectly right. Thank you. Another thing to correct in the, you will see a new version of the notes on the everyday. Okay, so I was given this, nicely given this ribbon. So actually, maybe this is why actually for this reason that the twisted ribbon is so interesting, is that the helicoid, which is the trivial shape, I mean the immediate shape you may think of if you say what shape does take a ribbon that is just twisted, and you will see that it can take all kind of crazy shapes. So if I mean this is easy to do yourself, you can see wrinkles with, along this direction. And if you twist more without applying too much tension, you will see triangular facets here. And if you pull a lot, you can see that it buckles along this direction so that you lose it becomes more cylindrical. Okay, so the phase diagram of the twisted ribbon is complex and not yet understood. Maybe all because of this. Okay. Now,
so I had a quick question. So the twisted ribbon parameterization that you've chosen, right?
Sorry?
The twisted ribbon parameterization that you've chosen. So you chose a particular parameterization
the A tilde?
For the twisted ribbon. A
yes,
of U
yes,
at U.
Yes.
But so that particular parameterization gave you non-zero Gaussian coverage.
Yes.
Right. So is it obvious that this thing is parameterization independent?
Gaussian curvature?
Because you're trying to show that ruled surfaces have Gaussian curvature 0, which is what you show.
Yes.
I'll phrase my question.
No, it should not depend on the parameterization. It should just depend on the shape. Yes. Yes. You have this red frame and this orange frame, and these are the main results. Okay, so now I will show pictures. Enough calculation for today, so so this was not a blank screen, this was a black presentation. Okay, so I've said a lot about the metric. Now there are many ways to make and people have tried to make programmable shapes. I don't know if there was something here. Maybe this. Wow, amazing. Thank you. So people have playing. We've seen that the metric is strongly. The surface, the shape, Gaussian curvature is strongly constrained by the metric. So this means that you can, by prescribing a metric to the surface, you can make it take a shape that you want. And so there are several ways to prescribe the metric. And what is also nice is you want to make it programmable, so that you take a flat sheet and then you apply some external stimulus, and the sheet takes the desired shape. Okay, this is what you want. So this is one way to get it. You have a gel that can expand when you put it in a solvent. Okay, and it can expand in a controllable way. So here the gel is made from a mixture of two solutions, and one expands more than the other, so that the expansion will not be uniform. And the shape can take this, you can activate the metric, and the shape can take this, you can program a metric with a positive Gaussian curvature and end up with this shape. Okay. Note that in this problem, you not control the full metric. You can just multiply the metric locally by a constant. Okay. Here is another example with inflatable fabric. So this is flat, and when you inject air, you can get this shape or this shape, depending on the way that it inflates. Okay. So in this case also, you don't control the full metric. But now the metric is not the metric change when you apply the pressure. It doesn't go from flat to some constant times flat. It has a direction, and it inflates differently along the two directions. Okay, so the metric now has two parameters. Okay, but still you don't control the full metric. And so then came the question of, can you make any shape with this, or can you make any yes, can you program any shape with this process? And so this leads to an interesting inverse problem, which has been shown to be solvable. So there is the paper Aroni 18 and Mirinyasti and collaborators 19 have shown that this model always that you can solve the equation for finding actually how to design your metric. This kind of metric, the metric that has a local director everywhere to recover any shape. Then an interesting problem that appears is also if you take a simple plastic bag and you turn it. Okay? And in this case, during the tearing process, there is a local expansion of the metric. And actually what happens is that here the edge, so this is X, no, this is, sorry. This is Y and this is X, and the sheet lies in that, I mean, you turn it along this direction, and in the tearing process, actually, the sheet expands here, and you get GXX, which is larger than 1, and also it's a function of Y. It's a decreasing function of Y. So the sheet far from the tearing zone is unaffected, but close to the tearing zone, it inflates in this direction with a factor that is, yes, that decreases with Y. And this gives rise to this, so this is not programmed, this is what you get out of the tearing process. And this gives these nice fractal patterns close to the edge. Okay? And this has been shown, repeated in simulation and shown also to correspond to what is what happens at the edge of some leaves. And so this is really, I mean, leaves are not torn, but this comes from a growth process. Okay, so this shape can emerge just from when you see this shape, the idea is that when you see this kind of shape in nature, you can wonder about what is the process that makes them look like this, because the shape is complicated. So if you want to program this shape directly, this is complicated, but actually it comes out of a very simple metric. Okay, and maybe something that will be discussed next week by Efrati is the fact that, of course, you can have shapes with you can have non-flat shapes, so shapes with a non-flat metric, and shapes can also have a non-flat curvature, and it happens that these two are incompatible. They do not match with each other, and this appears a lot in plants, and so this will be discussed next week, I think. Okay, now I will move to a subject that I like a lot, which are elastocapillary phenomena, because putting sheets in contact with liquid interfaces is a nice way to apply, to load them in a very soft manner. Okay, so I give, so for these experiments on elastocapillary phenomena with sheets, we can distinguish between two types of sheets have been used. So there is the first class, so I give here an example for PDMS, and the second class with polystyrene sheets. You see that the main difference between these sheets are the different thickness. So here you have 60 microns, here you have 100 nanometers. Okay, so it is very large thickness difference. And as a function of this, so here I put, okay, so the Young's modulus is also very different. Then when you look at the stretching modulus, so the moduli that are interesting for sheets are the stretching modulus, which are here. So these are comparable, okay? But then when you look at the bending modulus of these, the thick sheets will be much higher, okay? Because they have the same stretching and they are thinner, so they have a larger, larger bending modulus. And from the bending modulus, and so you see that these sheets, they are in contact with liquid interfaces. So if we take, as an example, as a reference, the air-liquid interface, we know that the surface tension of the air-liquid interface is of the order of 0.1 Newton per meter. Okay? So if you take you see that this value is much lower than the stretching modulus. So it means that the air-water interfaces will not be able to stretch these sheets. And then to compare it, we want to compare it to the bending modulus, but of course they are not of the same, they don't have the same dimension, so we cannot compare them directly. And to do that, we have to define, actually comparing the two defines the bendo capillary length, which is defined as square root of B over gamma, the surface tension. Okay, and this tells you, this length, this, okay, roughly tells you the radius of curvature that the surface tension will be able to impose to the sheet. And here you can, I gave the values of L, the bendo capillary length here. Here you see that it is just 0.7 millimeter. Okay? And if you look at these sheets here, so these are PDMS sheets of the first, correspond to the first line. Here the size is of the order of 1 millimeter because you deal with drop, and so you want to be below the capillary length. You know, otherwise the liquid will just flow. So in this case, the bendo capillary length is of the same order of the size of the sheet. So it means that the surface tension is barely enough to bend the sheet. So it cannot bend a lot, but you can make this nice, what was called capillary origami. Okay. And what's funny is that this experiment, maybe the first experiment that I, on this, of this group on this subject came out the same year with very different, okay, you see the thickness here, and here you are in the second range, so you still have millimetric sheets. So here, okay, what do you see here? This is a sheet that is floated on the liquid interface, and then you put a drop on this sheet. Okay, so particularly complicated setup, nightmare for theoretician, but okay, this is the first thing they did. So what you see these wrinkles, and the size of these wrinkles is much smaller than the size of the sheet, and you see that the bendo capillary length here is 2 micrometers. Okay, so you can, these sheets are very easy to bend at under scale. No, they take it, not an important role. They take a millimeter size because the capillary length is 2 or 3 millimeters. So it means that you can have a drop standing of 2 or 3 millimeters high on the table without flowing. If you want to put more water, then it will. So this is they didn't want gravity to play a strong role here. Oh no, for the sheet it's even the sheet is much thinner. The weight of the sheet is very small here. There are some examples where the weight of the sheet matters, but it's, it will not in what I will present today. Here? No, this is the evaporation. This is the amount of liquid. So they put a big drop. This is you see it here. Yeah. Now you know that it's evaporation. They put a big drop on the sheet, and then they let the drop evaporate. And as it evaporates, it shrinks, and so you can close the origami this way. Okay. Then I will move to the second chapter, last, on wrinkling, mainly. So now I will have another. I wanted to base this on the Euler buckling, but there is no Euler buckling has not been treated in the first in the lecture by Ajit before. So I will very briefly review Euler buckling. So buckling is what happens when, so I mean, why do all these motifs? I mean, on the here, there are wrinkles appearing on these sheets, and we want to understand these wrinkles. Okay, so this is the first. This will be my first goal here. So, yeah, I need to erase a bit more. So the basics of, I mean, basically wrinkling is very simple. It's a kind of Euler buckling. So we have discussed the stretching modulus. The stretching modulus tells you how difficult it is to stretch or compress a plate. So stretch or compress, okay, this is very difficult. The thing is that plate, they do not respond the same way under traction and compression. Under compression, you have another mode of response that is possible, which is just buckling. Okay? In buckling, when I do buckling here, I see a single big buckle, meaning that the wavelength of buckling is just the distance between the two ends of the sheets. Okay? Why? Because the sheets then here just want to minimize the bending energy. When I buckle, I convert the energy coming from compression, so this is stretching energy, into bending energy. Okay? And in order to minimize the bending energy, you have to have a radius of curvature that is as large as possible. And so to do this, I kind of maximize the wavelength. So I do one big buckle. So here I will start with wrinkling. And so this will be 2, 1, 1 wrinkling. And I will restrict myself to a scaling analysis here. So when you do wrinkling, you have a wrinkle pattern is characterized by an amplitude A, which is usually difficult to measure. I mean, from these pictures here, you cannot measure A, and a wavelength lambda that is typically easy to measure. Just look at the picture. Okay. Then the bending cost of this pattern, so I will write the energetic cost per unit area. So I have the bending modulus, okay, and then I have to multiply by the curvature squared. But the curvature squared is the curvature is just the second derivative of the height, which is A over lambda square. Okay. So you have this cost for bending. So then, what is the compression? Usually you buckle, you wrinkle because you want to compress the sheet. So what is the compression? This will be epsilon. I will write it as positive, but there is actually a negative effective strain, meaning that the plate gets shorter if you look from far apart. And actually this effective length is because the full length, so L0 is given by the integral of square root 1 plus zeta prime of S square ds from 0 to L. Okay, if the plate is of, if the end-to-end distance is L, the length of the plate is L naught. Okay, and so this is approximately, if I expand this square root, because if I do a small slope expansion, I will have 1 plus 1/2 integral 0 to L of zeta prime S square ds. L, yes, sorry. So if I look at the strain, at the effective strain, which is this actually this difference divided by L. So if I take L naught minus L divided by L, or by L naught, which is the same to the lowest order, this is of the order of sigma prime square, and sigma prime square is A square over lambda square. So this is epsilon. So this we will use a lot. This relation is that if the simplest way to describe wrinkles is to assume that the sheet is incompressible. Okay, so all the excess length that you have in the sheet goes back to its rest length by creating these wrinkles. Okay, so there is no more compression, material compression. So this relation here should always be satisfied. So this gives you usually what you impose externally is epsilon, and what you and then you have to determine A and lambda. Okay, so this you can see this as a way as a constraint between A and lambda. So if you put it back in the bending modulus, I will write A square is epsilon lambda square. So this gives you bending is B epsilon over lambda square. So if you have only this energy, you want to maximize lambda. And this is why when you do buckling without foundation like this is Euler buckling, you want to maximize lambda, and you get lambda is equal to L over 2. Okay? Now, the sheet on the right is on a liquid. Okay? So in this case, it has a cost to create a wrinkle. It has a cost to move up or down. Okay? So there is an additional cost here coming from I don't know. Okay. I will move away from this example. Okay, I don't know for this precise example where the cost for deforming the interface comes from. I will review different kinds of costs later. But here I will take the simple case of imagine that you put a sheet on a liquid and you do uniaxial compression. Okay? In this case, there is a cost for deforming the liquid. So there is also gravitational energy, UG, which is rho g, and the cost of making these waves is actually A square. The cost of the energy that it takes to take this fluid here to here scales as A square. So now this is rho g epsilon lambda square. Okay, and if you put an elastic substrate on or any substrate, actually we will call this rho g. We'll call this the effective substrate stiffness. Okay, so you will have U substrate, which is K effective A square. Okay. So this works from the liquid, this works from the gel, and I will show after that in two-dimensional settings there are other means to set K. And there are other physical mechanisms that set an effective stiffness. Now that you have this, so you have U sub, which is K epsilon lambda square. So now what you have to minimize is not just U band, but U band plus U sub. Now you have a contribution that wants large wavelength and another energy that wants small wavelength. So they will, I mean, you have to optimize the two. So usually you have to take the sum and then derive it with respect to lambda and take the minimum. Okay, but what it turns out is that in this, when you do this, actually you can take a shortcut, and the shortcut is saying that U band is of the same order as U sub. Okay, this is exactly the same as summing and taking the minimum, except from some numerical prefactors coming from the derivatives. But actually, you can see that this, since we are only doing a scaling analysis, the prefactors are wrong anyway. So we can directly take the shortcut and use this expression. Okay. So if you do that, you have B epsilon over lambda square goes like K epsilon lambda square, and this gives you lambda is B over K to the power 1/4. So this is how the wavelengths are analyzed. And actually, this gives you a way when you compress a sheet on a liquid, since you know the density of the liquid and G usually, then you, except if you're on an unknown planet, but let's consider that you do things on Earth. Then this is a way to measure, looking at lambda gives you a measure of B, which is not that easy to measure actually for these sheets. Okay, so this is assuming that wrinkles have formed, but you can also look at the wrinkling threshold. So for this, you can do a linear stability analysis of the flat state with the Foppel-von Karman equation, or with the Euler-Bernoulli equation, which are the same here. But what is equivalent is to add a Lagrange multiplier to epsilon, and the Lagrange multiplier will be the compression strength, and so you will add U compression, which is minus sigma epsilon. Okay, and then you want to minimize the energy. So of course, when the energy, because you have to, then you have to determine, I mean, this way you will have to minimize over epsilon also. You see that here, the energy depends on, I mean, it depends linearly on epsilon. So you want epsilon to be 0. But then if sigma, so here the energy, sorry, the final energy here, you wrinkle will be, if you replace, you have square root of bk epsilon. Now that you have solved for lambda. And so here you will have U total, which will be the sum of the two. So you have square root of bk minus sigma, which is the compressive stress epsilon. And then you see that epsilon, once, as soon as this is, so epsilon here cannot be negative. So as soon as the prefactor is negative, then epsilon will increase. Okay? And since it depends linearly on epsilon, you do not know how far it gets, but you still have the threshold. So the critical sigma is square root of bk. And you do not know how it stops because this is linear in epsilon. So it never stops. And actually with Euler buckling, it's not easy because Euler buckling is subcritical, meaning that once you hit the threshold, then if you work at constant force, you go to a complete collapse. Okay, but if you do it at in-pose displacement, of course, you can have the, it will stop at some point. Epsilon is imposed. This is at imposed force. Yes. Okay, I will be very brief on the next. Okay, so these wrinkles, okay, you can form, and we have all these characteristics here for uniaxial compression. So you can, this experiment of uniaxial compression has been done, and this is what you get. So you get first this wrinkle, so this is a side view, but you see that as compression, as you put the ends closer together, the compression actually localizes in a single fold. Okay, so this is a nonlinear, this localization here is a nonlinear effect that you can actually easily understand from a simple scaling analysis. Okay, you can compare the scaling of putting a single fold here compared to wrinkles over all the sheet. And localization appears, so this is a bit striking, but localization appears when the compression distance, so L naught minus L, is L naught minus L becomes larger or comparable to the wavelength lambda. Okay, so this is, I mean, this criterion is a bit strange because this is not, this is an intensive quantity. It doesn't depend on the size of the system, but this one is extensive. Okay, so this means that for a very large system, it should almost form a fold immediately. And you will never, it will be very hard to see the wrinkles. Yes. Yeah, you can find a family of solution, and you see that. I mean, if there is a barrier for if you take into account the barrier, you can directly see the fold. Yes. Yes, I mean, if there is, I mean, you can know that if for a large system, when you hit this threshold, you will already be at finite compression, and then you will jump to the fold because the compression will be larger than lambda, and you will never see the wrinkles. Yes. But if you can do it in a controlled way, you should be able to see this, and we see this. So we see that the amplitude increase, but there is a modulation of the amplitude, and here the width of the pattern here it decreases up to a fold, and these two have been described. So actually, I show here. I mean, you can find interestingly, you can find the exact solution, which is here. I don't cite. There is a paper by Odoli in the same year that is more an expansion around the threshold, and which, after reading, actually made a tutorial from this paper, and it is maybe more, I mean, not more instructive, but you learn from this paper because it characterizes the width of this region. I mean, the modulation in a more in a simpler way. You know, this is when you have this exact expression, then you have to analyze it. And so, yes, here I don't give the expression of k. So k is 1 over lambda, okay? And kappa is the localization parameter. Okay, and this is what happens. I mean, if you do it on a gel, you can have a different kind. I mean, gel, you cannot, the sheet cannot slide on the gel. And so you have another kind of localization, which is here. So since you have, I mean, linearly, these systems are equivalent, but non-linearly, they are different. And this is what you, actually linearly, they are equivalent. I'm not that sure. I don't think, I mean, it's not rogy, but there is some kind of stiffness. I'm not even sure that the mechanics is that simple for jazz. Actually, what you see the same thing. Okay, it's A square. There is no, I don't know if it, okay. Great. Okay, so now let's move at two-dimensional buckling. So actually what happens in the variety of systems that you can make with these sheets and elastocapillary phenomena is that what favors large wavelength is always the bending energy, which is here. Okay, bending energy is always the one that penalizes small wavelength, and then there are multiple effects that can penalize large amplitudes. So many sources of K. And this is an example of them. So this is one of the foundational papers for wrinkling. And the idea is this one. So here, this is just a plastic sheet that is taken on both sides and that is extended. And this stretching creates, this compression in the center, and you see these wrinkles. Actually, the origin of the compression here and the origin of the wrinkle has been debated. I don't know if it is settled actually, but the stress field in this case is very complex because you clamp the sheet so it cannot move inside on the edge. So the stress field is, maybe this is a good thing to do some Phoenix simulation. We should trade, I mean, for the next school, we can have, we can discuss this time and then the next one will be amazing. Okay. So the stress field is very complex, but the wavelength is simple to understand. And for the wavelength, there is bending, but then you see, okay, I don't know if I want to make a drawing. Wrinkles will be like this. You know, you will have peaks and valleys that will go like this in between. Okay, but then since you apply some tension in the sheet, when you look at a wrinkle from the side, you will see this with the tension here. And this has an energetic cost because you extend the material by creating the wrinkle, actually. Okay, so here U tension, due to the tension, will be the tension times so it will be T times the extension that you create, and the extension is A over L square. Okay, so this A over L square is epsilon. This is the same as A over lambda there. Okay, but this is T over L square times A square, and this is the effective K coming from the tension. Okay. Also, it has been another source is curvature induced stiffness, which is this time, imagine that you have a sheet that is for some reason placed on a substrate that is curved or that is curved. Imagine that this is what happens when you, okay, I don't have leaves strong enough here, but when you do this, you have wrinkles on your fabric, and they are curved because you don't have a flat infinite arm, usually. Okay, so in this case, you have this kind of wrinkles, and this here, because of the curvature, you create a strain. So here the strain is A over R parallel, where R parallel is the radius of curvature of the sheet in this direction. And so the stretching energy here is Y, so the stretching modulus times epsilon square, which is Y over R parallel square times A square. And this is K curve. Okay, I will stop. I mean, this is my last effective stiffness, but all this stiffness play a role, and why not others? Okay? And the worst case, of course, is when you have a combination of them in a system. You have some in some part and another in another part, and then you don't. I mean, harder to disintegrate all this. Okay, maybe I'll try to discuss cascades to finish. So do I have something about cascades? Yes, cascades. So cascades are a bit different. So cascades are change of wavelength as a function of the direction along the wrinkle. Okay, so you see here, what you see here is a sheet on a liquid, and I didn't tell you what happens at the edge of the sheet. So the edge is here, and you see that the capillary forces at the edge, they want to make the edge flat, so there is another contribution, I mean, another energy term at the edge that penalize departure from a flat state. And so the wrinkle, the wavelength is much smaller at the edge, and then you go to the infinite wavelength here, okay? You have this change in wavelength. And you have the same kind of change in wavelength on hanging curtains. So you have a nice example here. You see that, okay, let's take these two. It's nice that I have the pointer. Let's take this one and this one, okay? You see that, I mean, obviously I have two different wavelengths here, but as I go down, I mean, this one goes down, and then I mean, these two, I lose one wavelength here. So the idea is, okay, and now I can, if I take an infinitely long curtain, maybe at the end I will just have one big buckle like in Euler buckling, okay? Because I impose compression at the top. So to describe this, so this is what is called typically a cascade. And to describe this, so the paper that I will base myself on is Van der Paar 11. And they have introduced what they call the Wrinklen, which is the elementary building block that takes you from lambda to two wrinkles with a wavelength lambda to one wrinkle with a wavelength 2 lambda. Maybe okay, this is to do this. Okay. So you have this complex pattern that is here. So actually, the energy the idea is that what you gain by going from lambda to lambda. Okay, and what they come out with is a bending energy that is the same as before. Okay, because this is the typical energy of this associated to this wavelength lambda. I mean, lambda 2 lambda is the same, but then there is a stretching energy. The stretching energy is Y times, so it's not, it's y times the strain, but in the direction, in this direction L. And the strain in this direction L, you have to extend the sheet to go from this one to this one. You have to make this kind of shape somewhere in the system. And here you have, so actually there are two different cases. There is one where this is A over L 4, because you have L over L square, which is here, this is epsilon, we call it epsilon parallel square. This is when the sheet is not under tension. And then there is T epsilon parallel, which is T A square over lambda square if tension. Sorry, it's not lambda, it's L. And then if you do U band comparable to U stretching, it gives you L. Goes like, I won't do all the calculation, but you have this epsilon 1/4 T minus 1/2. This should be the energy because this is the ratio of and lambda 3/2. So this is if T equal to 0. And if T is non-zero, you have T, no. L. Why do I have this? T over Y. Oh, okay. Wow. Why did I do that? Okay. T, you have T, okay, lambda 4 over B. To the 1/2. Here I use the thickness, which is, by the idea, the thickness is thickness minus 1/2 is actually Y over B to the 1/4. If T non-zero. So T0 and T non-zero makes a difference because I mean in curtains you have the weight. Okay, so at the bottom of the curtains you have a little tension because you have no weight here. Okay, but at the top of the curtain we will have the weight of all the curtain that pulls, and so this is strong tension. So from this, actually they could go to deduced law like lambda is the distance to the top at some power, okay, nu, which depend on the two cases. Okay, and this can be seen in experiment. Okay, because here you have L as a function of lambda, so you can see this as a derivative. Actually, if you have lambda over L, this is lambda prime, and then you can have a scaling law for L. And this has been done, so the funny thing is that it has been done for curtains, but it has been done for graphene sheets. So you have a compressed graphene sheet and you can apply some tension and you can see actually this law. What do we have here? Yes, I will, okay. I haven't described these cascades. Actually, so this paper is earlier. I'm not sure. Not sure that it has been fully described in this, fully explained in this paper, but this paper has the theoretical explanation. So in the minutes I have, so I will go to other, let's call it, okay. Other patterns that can arise in compressed, I mean, after buckling. So one is, so this is a setup that I will come back to, but this is a floating annulus that is compressed by putting a surfactant outside so that the surface tension in the outer part is lower than the inner part, so the inner part is pulling, and this creates the wrinkles. And at some point, it may, so it forms these nice wrinkles. At some point, it should go to this shape. Actually, we may see it in the tutorial on Thursday. Investigate this. And this is an example of a sheet wrapping liquid droplet. And here you see that, okay, you don't even see the nice wrinkles. I mean, there are some nice wrinkles here, but on the top of that, there are big folds in this case. Okay? So in this situation, it is not clear that if the fold is of the same nature as this one. So I would say that this one is a mechanical fold. It comes from the nonlinearity of the problem. Okay, but it is uniaxially a compressed fold. I would call this, I mean, I haven't shown it here. I may show it next time, next lecture, but these folds, I would call them geometrical folds, meaning that they are places where the sheet wants to put a lot of material, and they are favored because they allow, here on the right, it's particularly, I mean, on the right, what you see is a circular sheet wrapping a droplet. So two perfectly symmetric objects, and they make this triangular shape. This is a bit weird. But here, to make this triangular shape, you need folds, okay? And not you need sharp folds at the corners and not wrinkles. And so what I will show, but what I will pretend next lecture is that these folds are here just to make these shapes, to make different shapes, but not because they are individually energetically favored over wrinkles. And I will conclude by this shape with the crumples. So this is another weird pattern that has been seen atop of wrinkles. So you see first nice wrinkles, and then if you push the experiment a bit further, so you have different experiments here. First, you put a sheet on a drop, an air-water interface with increasing curvature. First, you see nice wrinkles, and then you see this localization pattern. Here, you put a sheet on a liquid, and then you just push on it, and the same, you go from wrinkles to crumples. Here, this is maybe the simplest experiment. You put a sheet on your sleeves. You put a sheet on a curved interface, and you compress it, and you go from this to this. And here you have an inflated balloon. So this is at low pressure, and this is at high pressure. And you see here nice wrinkles, and here these diamond-like patterns. So we'll come back to them hopefully in the last lecture. The bottom line is that these patterns, this transition is not yet understood. There is no model for this transition. Some nice, interesting work to do. Okay, sorry for being late. I will stop here. And, oh, but because this has not been started. This is why. I still have 1 hour and 25. Yeah. Good. Thank you. Do you have any question?
Any questions?
K approximately 0 mean that in another?
Oh, it means, okay, so for this transition, at some point it was, if you look at the two first examples, it may have been thought that the Gaussian curvature plays a role, because Gaussian curvature is positive here, negative here. So it was in this problem, I mean, the authors wanted to know if the Gaussian curvature of that you try to impose to the sheet plays a role in this transition. And the answer is no, because they devised this. Actually, these were already existing experiments. And for the paper, they made this new experiment. They designed this with zero Gaussian curvature. So the interface is a cylinder. So you don't have this. And still you see the same effect. And this one is more, I mean, is maybe the easiest experiment, but the less controlled. In this case, you just control the pressure in the sheet, and then this is the balloon is just two pieces of material, two squares glued together, so it's less controlled. But yes.
Regarding equilibrium of the configuration, so there can be multiple stable configurations for a kind of loading, right? Like, I mean, the patterns, are they unique for a particular kind of loading that we apply?
Sorry, I didn't.
like the wrinkles or like crumples, if we apply a particular load, is the pattern unique? So there can be different stable configurations that it can obtain, right?
Different stable configuration.
Yeah, yes.
Yes, so okay, so maybe I didn't say it to, so in what I present, I mean, what I presented yesterday, today, and I will always, almost always assume that the system reaches its energy minimum. But of course, it depends on there are cases where it can depend on history, but it is always an assumption. It is not something that we can prove. We don't have the, usually we don't have the dynamics. I would say that we will care about the dynamics when we will have understood the statics.
Okay, if there are no more questions, we'll meet here at 2, not 2:30. Lecture starts at 2. Thanks, Vincent.